Next, let us move on to auxiliary potentials and Helmholtz equations. We start from Maxwell's equations in the frequency domain. Our goal is to determine how the electromagnetic fields behave when the current density J and the charge density ρ are given. To do that, we also need information about the medium. Here we consider the simplest case. The medium is homogeneous, so epsilon and mu are constants, and it is non-conducting, so sigma is 0. Under these assumptions, Maxwell's equations can be rewritten in terms of E and B. However, even in this form, they are still difficult to solve directly, so we introduce auxiliary potentials. First, look at the equation the divergence of B equals 0. From vector calculus, we know the identity that the divergence of a curl is always 0. Therefore, it is natural to write B as the curl of a vector field A. So we define B equals the curl of A. This A is called the vector potential. Next, we substitute this expression into Faraday's law, equation 9. Then the curl of E becomes minus j omega, the curl of A. Because the curl operator is linear, we can combine the terms and write the curl of E plus j omega A is equal to 0. Now we use another identity. The curl of the gradient of any scalar field is always 0. Therefore, E plus j omega A can be written as the negative gradient of a scalar potential phi. This negative sign is simply a convention. So we obtain E equals minus j omega A minus the gradient of phi. In this way, B and E can be expressed using the vector potential A and the scalar potential phi. These are what we call auxiliary potentials. So instead of finding E and B directly, we first find A and phi, and then recover the fields. Now let us derive an equation for the vector potential to determine when sources are given. We substitute B and E, written in terms of the vector and scalar potentials, into equation 11. After substitution and expansion, we obtain an expression containing the curl of A. Here we introduce a vector differential operator, nabla squared A. Its definition is the gradient of the divergence of A minus the curl of A. This is not the Laplacian operator. Actually, the Laplacian acts on scalar fields, but this operator acts on vector fields. However, in Cartesian coordinates, it acts component-wise, so it looks similar to the Laplacian. Using this notation, we can rewrite the equation into a more compact form. So far, this equation is still not closed because it still contains phi. At this point, we should notice that the auxiliary potentials are not unique. Suppose that A and phi give particular fields E and B. Now, for any scalar function f, we can define A prime equals A plus the gradient of f, and phi prime equals phi minus j omega f. If we calculate the curl of A prime, we obtain the curl of A because the curl of a gradient is 0. So B remains unchanged, and if we compute this expression, all additional terms cancel and we obtain the same E. Therefore, E and B are invariant under the transformation of A and phi to A prime and phi prime. This is called the gauge transformation. Therefore, there are infinitely many pairs of A and phi that produce the same fields. So we can impose a convenient gauge condition to the potentials that make the equations easier. A very useful choice is the Lorentz condition. It is written as the divergence of A plus j omega epsilon mu phi equals 0. If we impose this condition, the gradient term disappears, and the equation for A becomes a very simple form. This is called the vector Helmholtz equation. Next, we derive the equation for the scalar potential phi. We substitute equation 14, E fields expressed in terms of the potentials, into equation 10, Gauss's law. Then we obtain this equation. Using the Lorentz condition, we can eliminate the divergence of A. As a result, we obtain this equation. This is the scalar Helmholtz equation. In practice, we often do not need to solve the scalar equation separately. If we solve for the vector potential A, then phi can be obtained from the Lorentz condition. So the main equation to solve is usually the vector Helmholtz equation. Let us summarize the procedure. The source terms J and ρ generate electromagnetic fields. In principle, we could solve Maxwell's equations directly, but that is difficult. Instead, we solve Helmholtz equations for the auxiliary potentials A and phi. In practice, it is sufficient to obtain only the vector potential A. Once A and phi are known, we recover B and E from these equations. So we take additional steps using the auxiliary potentials, because this approach is often easier than solving Maxwell's equations directly. This is the basic idea behind the use of auxiliary potentials and Helmholtz equations.